Hello, this is the second example to support your understanding of how to determine all of the roots in exact form. A higher order polynomial if you're not given at least one root or a linear factor that it's divisible by. Again, we need to generate a list that is a ratio of the factors of the constant term divided by the factors of the leading coefficient. And from there, we'll test the possible set of roots to find at least one real root. For this, it's a cubic. As long as I find one real root, when I divide it by the corresponding linear factor, I'll be left with a quadratic. So I know I could then use either factoring, quadratic formula, or completing the square to find the remaining two roots. Those remaining two roots could be complex roots, they could be irrational roots, they could be real roots. But again, it's a cubic, so it does at least have one real root. So let's go ahead and generate what is called our P over Q list, where we're going to list the factors of the constant term, and it's 1, so that would only be plus or minus 1. But then we've also got the factors of, in this case, the leading coefficient is plus or minus 1, also plus or minus 2, and also plus or minus 4. So what is this list that we need to test, right? What are the possible roots? Some of these are actually fractions. But we do have the 1 and the negative 1, so we were going to have 1 and negative 1, but we'll also have plus or minus 1 divided by the plus or minus 2. So we'll need to test 1/2, negative 1/2, and likewise 1/4 and negative 1/4. So this is a possible list. I always start with testing 1 and negative 1 just because they're the most straightforward, and let's see what happens. So what happens when we plug in 1? So we're going to test x equals 1 to see if we get out a 0. So 4 times 1 cubed plus 1 squared minus 6 times 1 plus 1. So this is just 4 plus 1, which is 5, minus 6. So that'd be negative 1 plus 1. That equals 0. So therefore, that x equals 1 is a root. And I love when it works out like this. And x minus 1 would be the factor that corresponds to that root, because I found it on the first try. So let's go ahead. I'm going to use the area model to actually do, in this case, the dividing of the polynomial. And I know that I'm taking a cubic down 1 degree down to, in this case, a quadratic. And quadratics have up to 3 terms, and so that dictates that I made 3 different columns in my rectangular area model. And now again, I'm thinking about the sum of what's inside that rectangular area model has got to be this original cubic. We always place the first term, the 4x cubed, in this box before we again start the process of figuring out what is this quadratic factor. So if this side dimension of the area is x, we must be multiplying it by 4x squared to get an area inside of 4x cubed. Likewise, 4x squared times negative 1 is negative 4x squared. Now again, we want the terms that are along this diagonal will be like terms. We want them to add together to only be 1 x squared. And right now we have negative 4 of them. So thus we'll require it to be a 5x squared, making the top dimension here 5x. 5x times negative 1, negative 5x. Now again, now we need them to combine along the diagonal here to be a negative 6. That makes this negative 1x, making the top dimension negative 1. Negative 1 times negative 1 is 1. And again, I knew that these would be the same because I had already tested that there was a remainder of 0, meaning it was a root. And then that thus means that I did my, in this case, factoring using the rectangular area model correctly. So now, in this case, I have a quadratic, right? I could think of my function now. This is the same thing. My original function, which was this cubic, is really the same thing as x minus 1 times that quadratic factor, 4x squared plus 5x minus 1. And if I want to find the remaining roots, I need to think about, well, what are the zeros for that quadratic factor. So I like to first always check, is it factorable? Does something multiply to -4, right? Because 4 times -1 is -4, and then it adds to 5. So I think it could be 1 and 4, right? Because 1 and 4 do multiply to a 4, and they would add to a 5. But the only way that they would add to a 5 is if they were both positive, and that would not multiply to a -4. So this is not factorable. And if something is not factorable and it's a quadratic, we could use quadratic formula, or we could always complete the square. So in this case, we'll use quadratic formula. Since the leading coefficient is 4, I will not complete the square. So let's go ahead and see what are the zeros for that particular quadratic. So -b plus or minus radical b squared minus 4 times a times the c value, which is a -1, all over 2 times a. So -5 plus or minus radical 25, and this will become a plus because of the negative and the negative, and so it'll be plus 16 all divided by 8. And so -5 plus or minus, and now 16 plus 25, I believe, is 41, still underneath the radical symbol, all over 8. And again, just double checking that, yep, that would be 41, which is, in this case, a prime number, so I won't be able to simplify this any further. And this, in this case, is a real root. So this particular cubic has 3 real roots. These roots are just irrational numbers, but they are real roots. They are real roots because irrational numbers are also real numbers. Now, if I were trying to get an approximation for what its value is, it's like -5 plus approximately, well, it's going to be larger than 6 because the square root of 36 is 6. And it's going to be, though, smaller than the square root of 49, which is 7. So maybe this is about 6.5 divided by 8. And so if I was trying to get an approximation for what this might be, it's about -12 perhaps divided by 8. So that would be what is that actually? Gosh, -12, let me do that, divided by -8, and this would be 3 times 4. And this is, again, 4 times 2, and so the 4's cancel. So, again, we're looking at about -1.5. And then the other one, -5 minus approximately 6.5. So that would, and again, in this case, that would be the same one that goes with the value that I had above, because this one should have been a positive. So I should say when it's plus, that's the one when it was minus. When it was plus, that's going to actually make about 1.5 divided by 8, divided by 8. So again, a decimal, something very, very small. But all of those, that work helps you to generate a sketch. And that's what you're going to be doing in the lesson today. So let's go ahead and generate our sketch. In this case, we found a real root at 1. So this will be 1. There was a real root at 1. Our a value was 4, which is greater than 0. This was a third-degree polynomial, so I know that it will start and end in this type of fashion where it's starting in the negative in this quadrant down here before it finishes up in this quadrant. And then we've got a little bit of an idea of the fact that we're going to have like about a -1.5 root. We'll also have a very small positive decimal root. And then I can generate my sketch. Now again, I've got a y-intercept here of 1. And this is a sketch. Again, in this class, we're only generating sketches where we can find accurately the values of the x-intercepts and the y-intercept. However, to understand what the local maximums and local minimums are in between these points, that's something that you'll learn about in calculus.